Hello, Math 133 students. In this video, I'm going to go through the flow chart in regards to confidence intervals for Chapter 9. So when you look at a confidence interval problem, if it asks you to construct or build a confidence interval, then you're going to have one of two options. In Chapter 9, that is. You can either be working with proportions or you could be working with means. Now, if it's a proportion problem, you're going to look for, well, proportion. If you see the word proportion somewhere in the problem, or percent. If it's a survey, or if they talk about polling, we polled readers, we polled all adult Americans, and this is what we found. So if they're talking about any of those things, then that will mean that you are doing a one proportion z-int. And of course, that's what it is in the calculator, the one prop z-int under stats and then tests. Now the formula for a one prop z-int is p hat plus or minus z alpha over 2 is a little subscript, and then the standard error of the p hat. So it'd be p hat 1 minus p hat all over n, what we learned in section 8.2. So that's the standard error. So the z times the standard error creates the margin of error. And then this is your point estimate over here. So it's point estimate plus or minus margin of error. Now your critical z values, right? Your critical values are plus or minus z alpha over 2, or really just z alpha over 2. And you find those either with inverse norm. Right? You would do inverse norm alpha over 2 comma 0 comma 1, right? Because alpha over 2 would be the area in your left tail. Or you could use the bottom row of the t-table. Now, not all of them are available in the bottom row of the t-table. Only some of them are there. But if it's in there, you're welcome to use it. The parameter that you're making an interval for here with these critical values would be p, the population proportion, right? So p hat is a sample proportion. P is the population proportion. That's a statistic right there. That's a population value over there, a parameter. So we don't know what the parameter is because we can't poll all adult Americans. So we poll a sample of them. We build this interval with p hat in the middle, and that's where we think that the parameter will fall. This was section 9.1. And on our gold packet, if I open up the gold packet so you can see it, it's right here. It's in page 300, and it's this first box on page 300. That's where the critical information is. So you can see your point estimate is p hat, which is x over n. There's your formula. It's one prop z-int. All right, so this would be page 300, first box. Right. Now, the only thing that changes for these particular confidence intervals, if I open to them, you can see under the requirements, the random and the independent parts are the same, whether you're talking about proportions or talking about means. What does change is the normal requirement. So to be normal, you would need n times p hat times 1 minus p hat to be greater than or equal to 10. All right, now what about a confidence interval for a mean? So that'll be for a t-interval. And you're going to look for things like, well, I mean, first of all, if the mean and the standard deviation are sitting in the problem, that's always a good sign. What if they gave you a table of data? So if they give you a table of data, that's a sign that that needs to be done. Right? So the mean, the standard deviation, table of data. And last but not least, the other word you're going to see is, of course, mean is a form of average. So if they discuss averages a lot in the problem, then this is the one they're referring to. All right, now the formula for this one is x bar plus or minus t alpha over 2 times the standard error of the x bar. So s over the square root of n, what we learned about in 8.1. So you take your critical value times your standard error, and that creates your margin of error, these two things multiplied. All right, so your critical value is plus or minus t alpha over 2, which you find either from inverse t, and you would use alpha over 2 and then your degrees of freedom, or you would use the t-table, right? So you go to the alpha over 2 column, and you go degrees of freedom is n minus 1 for your row, which I forgot to put anywhere in here. So let me just make a little note. So note df is n minus 1. Now the parameter we're making this interval for is the parameter that is associated with x bar. X bar is a statistic from a sample. It's a sample mean. So the population parameter for it is mu. It looks like a U, but it's mu. U with like a long tail on the front. So that's the population parameter. It's the population mean. This was section 9.2. And on page 300, it's the second box. So if you're looking to your gold packet, that's where you're going to go. Let me grab my gold packet real quick. Although mine's not gold, but you get the gist. It's right here. See, and then there's that formula for degrees of freedom right there. It's n minus 1. Now, looking down at the normal for proportions is pretty straightforward. Normal for means is a little bit more complicated. There's a lot of options. So it could just be given to you. And by that, I mean it's written in the problem. I will write it's normally distributed, and then you'll know. Or I could give a histogram or a normal probability plot. I could give you some kind of graph. Or n is greater than or equal to 30. So all three of those are options. So it could be given. It could be a graph, like a normal probability plot is the most common. Or it could be that n is greater than or equal to 30. That's an or equal to. So greater than or equal to 30. All right, some other things to note real quickly before we leave all this behind. Alpha and the complement, and the confidence level are complements. I was getting ahead of myself there. In other words, they must add up to 1. Right? Next, so for our interpretation, we would say we are blank % confident, and you'd put your C level in here. Right? Whatever your C level may be, if it's 90%, 80%, whatever. And that's your interpretation. We are blank % confident that the true population parameter is between the lower and upper confidence interval limits. Of course, you would never write this. You would write in, for the true population parameter, you would write it in context. Right? And then also for this part down here, the lower and upper confidence interval limits, you would actually write in the numbers. You would not actually say those words. But this is the general form. It's the script that you follow. So I could say interpretation script. So this is a script that you're kind of following to help you when you write your interpretations for confidence intervals. Confidence intervals always follow a basic formula, so always a good thing to remember. Confidence intervals follow the formula of the point estimate plus or minus the margin of error. I mean, if we look at these formulas up above, point estimate plus or minus, all of this part is your margin of error. Point estimate right there, plus or minus, and the z and all the stuff here, that's the margin of error. It's the critical value times your standard error, the thing we learned about in chapter 8.2 or in chapter 8.1. All right, last but not least, let's never forget there's some relationships going on. So sample size and margin of error. So if you remember that this bit back here is the margin of error, the sample size is in the denominator. So if the sample size increases, that means that the error overall will decrease. So let me say this. As n goes up, error goes down, and vice versa. Okay. Now what about the confidence? Well, the confidence affects alpha. So if you raise your C level, you lower your alpha. But if you lower your alpha, you're making your T or your Z, your critical value, get larger, which makes the error overall get larger. We covered this in 9.4. So if your C level goes up, then your error also goes up. If you want to be more confident, you swell the size of your interval and you'll be more sure that you caught that true population value that is unknown to you. So you don't know where this parameter or this parameter are. So if you make your interval bigger, then you're more likely to catch it. Right? So if you want to make your confidence go up, then you make your error go up, which also makes your interval larger. Oh, actually, I'm going to put that down here. If error goes up, that means that width goes up, right? They increase together. And so the interval is larger. And last but not least, one we actually didn't discuss directly in class, but it's there, which is the standard deviation or standard error. They're actually kind of related. So right here, it only matters for this one. This one doesn't really have it. I mean, it does in that standard error is right there. So that standard error part, that big square root part, and or this standard deviation in that numerator, or the standard error is the whole fraction right there. So that's the standard error. If it goes larger, right, if that standard error or standard deviation increases, you'll notice it's in the numerator. So if it gets larger, then that means your error over here gets larger because it's in the numerator, as opposed to n, which is in the denominator. So if your standard deviation increases, then so does your error. So if s goes up, then error goes up, right? You can see it because s in the numerator. Technically also, if standard error of the x bar goes up and or standard error of the p hat, either one, if they increase, then so error goes up. They all kind of go together, right? Standard error is this bit of the formula right here. That's the standard error. So if it gets larger, then it's going to make the whole margin of error, this back half of the formula, get larger. So that's what I'm saying right here. Right? If s goes up, then error goes up. If standard error goes up, then error goes up. Right? Standard error is just a piece of margin of error. That's where it comes from.